break. Okay, don't try to collect. We'll collect during the break. Just make sure that you have the papers. Don't write anything else on the papers because it will be against our evaluation. And it doesn't matter whether you solve it correctly or not. So don't write anything more because this is the example that I'm going to work on. So I'll start by this example anyway. Previously, we have seen how to make convolution graphically, right? We know how to make the convolution. We flip around one of these two signals and then slide it over the other one. But there is a tricky situation here. And that tricky situation is that this signal, h of t, the impulse response, has impulses. Okay? It's not like the regular shape, for example, like x of t, with a ramp, with some box shapes, with sinusoids, whatever, positive or negative, it doesn't matter. But this one has impulses, and these impulses must be handled separately. There are a few things that we will see this hour, and it will be a list of properties in linear and time-invariant systems. A property of Lti systems, which we will see, we will just list down all these things, is that if any of these signals is consisting of a combination of several signals, then those separate signals can be separately evaluated for the convolution. What I mean is this. This x of t consists of a single entity anyway, so let's not separate it into other things. But if you have an h of t consisting of an addition of separate parts, then you can make the convolution with separate parts separately. So if this is, for example, h1 of t plus h2 of t plus h3 of t, like this, this is h of t, combination of three separate pieces. By the way, what I think of, what I have in my mind is that one piece is this impulse, one piece is this rectangular shape, and another piece is this impulse. Then the result is, according to the distribution property, according to the linearity of linear time-invariant systems, it's a linear combination of x of t convolution with h1 of t plus x of t convolution with h2 of t plus h of t, x of t convolution with h3 of t. Okay, that's what I mean. You can do this. So whenever these pieces can be handled separately, please handle them separately. It could be the case that this figure could be something like a rectangular shape and a triangular shape, for example. First convolve with this rectangle and then convolve with this triangle separately, and then add up the combination. Okay, that's a good idea to do. So this is the first thing that I want to point out here. The second thing that I want to point out is that I suppose, or I hope that you already know how to convolve this rectangle with this rectangle. You flip around and then you slide. The amount of slide determines the output. So let's think of this part, which is the middle part, let's assume. X of t convolution with h2 of t. And that part is the convolution of this rectangular shape with the same rectangular shape. When you flip around one of them, let's do here, you obtain the same figure. Okay, it's the same shape. What you really need to do is you need to slide this to the left and to the right so that the flipped around, which is the same, and the slided versions overlap with this first shape. When this rectangular is flipped around, the amount of slide that starts overlapping is somewhere here, where this is -1, this is -1, and this is -3 then. All right? This much to the left will start overlapping, and then you must proceed to the right. Going further to the left makes no overlapping. So how much overlap does that correspond to then? What is this overlapping position? I'm going to draw. I'm drawing which time instant, which shift instant. How much shift is there between this, which is the same as it's flipped around, and this? What is the amount of shift? 2. It's minus 2 in fact. You shift to the left by an amount of 2. So you start overlapping at minus 2. From minus 2 and onwards, if you shift this one to the right more and more, they will overlap more and more, and the maximum will be reached at the shift is equal to 0, because they will completely overlap over there. Okay? And what is the multiplication at that point? The multiplication of these two will be the same itself, exactly the same figure, and the area under it is from minus 1 to 1 of 1, which is 2. The area of this rectangle is 2. So it linearly, for this shape of course, it linearly increases to 2. All right? And then afterwards, after reaching this complete overlap, if you go further, the amount of shift will reach to 2, where the minimum overlapping occurs, and after 2 there will be no overlap. So it will decline back to 0 at 2. So this is the shape, particularly for the convolution of this rectangle and this rectangle, which is h2 of t. But of course we need other convolutions as well. X with h1, which is this impulse at minus 3, and x convolution with h3, which is another impulse at plus 3. So how are we going to do that? It's quite difficult to think of the multiplication of two shapes if one of the shapes is just an impulse. Right? What is the multiplication of a shape with an impulse? Well, it's another impulse, and the area under the impulse is something. So you can think of still sliding geometrical interpretation of convolution, but I don't recommend that. I want you to think of it like this. This thing, let's consider this, H3, this impulse. This impulse is an impulse response. Remember that. Always remember that. You can always think of it like this. So what does it mean? An impulse comes in, and the output is this. What is that? Another impulse at 3. A unit impulse at 0 comes in, and the system output generates an impulse at 3. What does that mean? It is shifted by 3. Here it is 3. Yeah. Okay, but it's a shift. That's the critical idea. It's correct that it's a shift. As a matter of fact, this system, let's forget about everything and let's only consider this kind of a system. H of t is this. What does it say? It says that the system is just a shifting system. So impulse response is another impulse shifted by 3, or you can think of it like this. You can even write the input-output relation for this system. It is such a simple system. It is saying that y of t is equal to x of t minus 3. That's it. If the input is x, the output is x of t minus 3. That is a delay system, nothing more and nothing less. Just a pure delay system. In fact, if you apply an impulse, if you put delta in terms of x instead of x, that is how you evaluate the impulse response. You input an impulse. Let's input an impulse. X becomes delta. Then y becomes h, which is the impulse response. What is h of t then? H of t is delta t minus 3. That's how you find the impulse response. Instead of x, you insert an impulse. That's how you find its response. And the response is delta t minus 3, which is this. And that is impulse response. So it means that the system input-output relation is y of t is equal to x of t minus 3. In that sense, it's quite easy to find the response of this system to any other input. Suppose that our input is not an impulse, because if it were an impulse, then the output would be this. But suppose that the input is this rectangle. This is x of t. Then from the system, what will be the output? Y of t will be x of t minus 3, which is 3 shifted version of the same input. This 0.1 and minus 1 points will be shifted towards right by an amount of 3. So it will start from 2. The center will be shifted by 3, and everything will be shifted by 3. This 1 will correspond to 4 then. So this is the output. This gives us a very good idea to about how to evaluate these things. Please don't forget your quiz. Warn your friends, please. Okay. So if there is an impulse somewhere, the easiest way to think of the convolution is you take the picture, you take the signal, which is this one, and you shift this signal by an amount of the shift of this impulse. And then that means the output. That is the convolution result. So convolution with an impulse is simple then. You don't really need to do anything graphical. You just need to shift the signal. You shift this signal here, around 3. That is the convolution of this thing with this impulse. That's it. Then this is one component, which is, let's say, the component A. This triangle, the convolution of two rectangular shapes. Let me erase this, and let's now think of convolving the same input signal x of t with this impulse at 3. What is the result? The result will be the shifted version of this rectangle around 3, starting from 2. Sorry about this border. This is 2, this is 3, this is 4. So this rectangle is the convolution of this rectangle and this impulse, which is part B. This is A, this is B then. All right, is that clear now? Similar thing will happen for this impulse as well. So don't worry about whether this shift amount is negative or not. It is negative, it means the shift will be negative towards left. It's not a causal system. Okay, something is going backwards. It's not a time delay system, it's a time lead forward system or something like that. So this portion, if you call C, is the convolution of the same rectangle, this time with this one was with H2 of t, this is H3 of t, this is H1 of t that I'm drawing, which is at -3, the impulse of 1. Of course, always remember that if the magnitude of this impulse, if the area underneath, in other words, is something different than 1, then this thing will be scaled accordingly. For example, if it is 2, then the scale, the magnitude will be amplified by twice. This is already 1, that's why it is reflecting as it is. So the convolution of this and this impulse is a rectangle around -3. This is -2 and this is -4. So this convolution, this is this rectangle, shifted this time towards left. Okay? So what do we need now? We need to add up these three shapes because we have to combine. And the combination I'll draw here is this shape. This magnitude is 1 and this magnitude is 2, and this is y of t. A combination of two rectangular shapes, one shifted towards right, one shifted towards left, and the convolution of two rectangles is a triangle in between. Okay? So do you have any questions regarding this? Is it understood? This is one of the critical things where most of the students just fail in answering questions respect to convolution with impulses. This is how you convolve with an impulse. So convolution with an impulse is nothing then. It's not even a convolution operation. It is just taking the picture and moving it to the position of the impulse. That's it. That's the convolution result with an impulse. As for this linear property, x of t convolution h1 plus h2 plus h3 is equal to this. The same expansion, linear expansion, is valid for xt as well. It doesn't necessarily correspond to only h's. So what I mean is this. X of t convolution with h of t is equal to x of t may also consist of several different parts which you may individually consider. Instead of considering all of the picture all at once, you can do it this way as well. x1 of t plus x2 of t. Suppose it consists of two pieces. There are two portions of x1. Which is x1 and x2. You can write it like this. And similarly, let's assume that h again has three portions. Okay? So this convolution is equal to, it's like, this thing is therefore like multiplication. The cross convolutions of everything will appear here. x1 of t convolution h1 of t plus x1 of t convolution h2 of t plus x1 of t convolution h3 of t plus x2 of t convolution h1 of t plus x2 of t convolution h2 of t plus x2 of t convolution h3 of t. In fact, this was what I had in my mind originally. I thought of a quiz question which has x of t, something like this, and an impulse, for example, or a triangle, or whatever shape, consisting of two parts in x and three parts in h. But then I thought that the cross convolutional terms will be too many. There will be 6 items then. So it's too much. But you understand the idea, right? You get the picture. Graphical or impulse-wise convolution, therefore, is easy if you can split your signal into several portions, several manageable parts. And for each manageable part, you apply the convolution. Okay? Now let's erase the question. I just hope that you apply many convolutions graphically using the Java applet that I was talking about, but this impulse thing does not exist in the Java applet, so you cannot convolve with an impulse over there. But convolution with an impulse is, as you see, nothing. It's just shifting operation. No, it's there. During the break, we'll take a look at that from the internet. I'll show you. So we used then the property of linearity during the convolution. The property of LTI systems, let me give a brief list of these things, and after that we will be dealing with the implementations of these LTI systems. So for LTI systems, the first property that we may start, do you remember the properties that we listed out for systems in general? For example, memory was one of them. Unfortunately for LTI systems, there is only one memoryless system. If you're considering all the types of LTI systems. So let's write it. There is only one memoryless LTI system. That is with an impulse response of h of t equals k times delta t. What is that? The impulse response is the same as the impulse that we input, which means y of t is equal to k times x of t, by the way. And over here, there is no memory because the output is immediately the same value as the input. It is just being amplified or attenuated by a scaling factor of k. Why don't we have any other LTI system? Well, we do have other memoryless systems which are not necessarily LTI. For example, if y of t is equal to k times x square of t, which is the square of the value, then that wouldn't be a linear system, but it would be memoryless. But if it is an LTI system, we cannot think of anything else than this one. All the other things, even the impulses, will contain some memory. If the impulse response is to the right or to the left, then you have memory. So this is a relatively useless property then. It makes a not so important thing. Let me continue with another, for the time being, a useless thing, which is invertibility. The invertibility is still unavailable for us. We don't have it. But what you really need to do is, if h1 of t is your system that you want to invert, then you have to find another system with an impulse response h2 of t. And when you combine those things, or convolve those things, then the convolution will correspond to an impulse. So, which makes this. h1 of t is our system, and x of t is coming. Then the inverse system is here, if it is an invertible system, of course. The inverse system is here, which is h2 of t. And we know that if you cascade two systems, then you have to convolve these two to combine it to a single system. So these two things will correspond to our new system. And here we have the output, which is y of t, and it must be equal to x of t, by the way. And this dashed new block is our new impulse response with h of t. And that h of t is h1 of t convolution with h2 of t by cascading. And we want them to be equal to delta t. Then h2 will be the inverse system of h1. But as I say, we don't have the tools to construct an inverted system, the inverse system in other words. I'm just saying that you have to find them. I can give you one example of an inverse system. Let's make it 2. Suppose this is h1 of t. What is the inverse system of this? This system is a delay system, obviously. It is delaying the input by an amount of 3. So what is the inverse system? Yeah, it's another impulse response, another system with an impulse response at -3. And when you convolve the two, you have to shift. You have to shift this thing to the left by 3, which makes an impulse in the center, or conversely, you have to shift this thing to the right by 3, which again causes another impulse in the center, which makes delta t. But for the delta t thing, since the scale here is 2, you should have this scale to be equal to 1 over 2 or 0.5. You have to be careful about the scalings as well. So this is h2 of t, which is the inverse system of h1. I cannot say I cannot give any other example with the tools that we have for the time being. Yeah, sorry. Although I said I cannot give anything else, in the discrete time or in the continuous time, another inverse system was already given to you as an example. Let me remind you of that thing. Let's see if you will remember that. H of n is equal to u of n. This time a discrete time system. And the impulse response is u of n. Do you remember what this system is doing if its impulse response is un? Do you remember the input-output relation? What was y? It was equal to k from minus infinity to n x of k, the accumulator. So if the impulse response is a unit step, then it corresponds to an accumulator, the integrator in other words, in continuous time. And what is the opposite of an integrator? Differentiator. This time it's discrete time, so a difference operator is necessary. If this is h1 of n, then you have to immediately, without doing anything else, just by inspection, tell me that h2 of n is equal to a difference operator, and that difference operator is delta n minus delta n minus 1 in discrete time as an impulse response. When you convolve any signal with this h2 of n, what does it say, gives you? What is the input-output relation of this thing? It is simply yn is equal to xn minus xn minus 1, it means. And we know that this is a difference operator. And this difference operator is the inverse of this accumulator operator. They are inverses of each other. For this, the impulse response is un. For this, the impulse response is easier. Just apply delta n instead of xn. Apply an impulse, and you measure the impulse response. Replace x with delta, and h2 of n will become delta of n minus delta of n minus 1. That's the inverse system. These two examples and their discrete counterparts, the discrete counterpart of this one and the continuous counterpart of this one, they are the typical inverted systems, inverse systems. So if you cannot really totally understand this thing, please go through those things, and if you cannot do anything else, please memorize them. Because this is a very typical inverse system operation. All right? That's necessary. You will have to, you will encounter this thing in several places, including examinations. So you should better learn this or this. Okay. So we have seen Lti systems. Let's continue with the third property. That is causality. Is it a causal system or not? Causality is like this. If h of n is equal to 0 for n less than 0, or h of t is equal to 0 for t less than 0, then your system is causal. For example, let's think of this h of n. When you convolve this thing with any input, let's assume any impulse in the center. In fact, let's assume that the input is an impulse. Okay, that's the most simplest thing that you can think of. The input is an impulse. So what is the response? It's here. This is the impulse response. And it says that the impulse response has started to exhibit itself at -1 already before the input arrives. The input is in the center and the output is here. So is this a causal system? No. It has to be perhaps something like this, starting from 0 and afterwards. This is a causal system because an impulse is exciting the system. You perturb the system with an impulse, and the output comes afterwards. The impulse response is right-hand sided. Right-hand sided impulse response. The same thing is valid for continuous time systems as well. For example, if this is your impulse response, as you see, the response started to show itself before the impulse arrives at the negative time. So this is not a causal system's impulse response. This is non-causal. But if it is something like this, then it is, this h of t is causal. Okay? Because the impulse perturbs the system, it excites the system, and the system shows the response, the output, afterwards in time. So this is also right-hand sided. So causality is fairly simple to check in Lti systems. All you need to do is you check the impulse response. If it is right-hand sided, if there is nothing at the left-hand side, then it is causal. Stability. If you remember previously, stability was an issue and it was difficult to test the bounded input, bounded output stability. But with the knowledge of impulse response, the stability, bounded input, bounded output stability is simple. All you have to do is you have to take a look at this summation. For discrete time systems, or this integration for continuous time systems. Is it absolute summable? Is the impulse response in discrete time? Is it absolute summable? Or if it is in continuous time, is it absolute integrable? If these things are finite, then you say that it is bounded input, bounded output stable. And the proof of this is quite simple. I mean, where does this come from? I just wrote it down, and this is the key to the answer of the stability check. but it also has a proof. We know that. Let me prove it in discrete time, or let me illustrate the proof. It's not very complete. Y of n is equal to k from minus infinity to infinity, h of k, x of n minus k. This is the convolution we know. Suppose that x of n is bounded. If that is bounded, then I will continue with taking the absolute value signs at the both hand sides. Because of the equality, these two are also equal. And furthermore, from the triangular inequality, I'm saying that y of n is less than or equal to k from minus infinity to infinity, and I'm bringing the absolute value inside the summation. And since they are in multiplicative forms, I can write it like this. Okay? So y of n is less than or equal to that, because when the equality holds, some of the terms inside this summation could be negative, some others could be positive. You add them up and then finally take the absolute value. It is of course less than individual absolute values being added. That is a sort of a form of triangular inequality. So this inequality holds. And we claim that x of n is a bounded input which has a maximum value. Let's call this maximum value to be m at most. So x of n minus k absolute value is at most m, bounded input, and the bound is m, which makes this summation to be equal to m times this summation, k from minus infinity to infinity, h of k. Sorry about this thing. I cannot go any further. So this thing is, less than or equal to m times summation of hk in absolute value, of course. Okay? Which means that y of n is less than or equal to this. And we want it, this y of n to be bounded, which is less than infinity, and we say this thing is less than infinity. And how does it happen? It happens only if this summation from minus infinity to infinity, absolute value of hk, is less than infinity, which is the original constraint that we have. And this m is just the upper or upmost value of the input. So from here, we conclude that h of k's absolute summation less than infinity is a sufficient condition for having bounded input, bounded output stability. But it's not a necessary condition. That's something else, as you may guess. Necessary and sufficient conditions are different things. I'm showing you that if it is less than infinity, it is sufficient to claim that it is Bibo stable. The necessary condition, you have to think of that by yourselves. For the continuous time case, this will be replaced with an integral, and the outside integration will be an absolute value. If you want to take that absolute value sign inside the integral form, then it will be a less than or equal to, again, a triangular inequality. And a similar thing, a similar trick holds for proving the sufficiency. So these two are sufficient conditions for bounded input, bounded output stability. And that's the thing that we will see for today. The necessary condition, or whether these two are necessary or not, will be a different figure, which we will not be interested in for the time being. And the next thing, other than stability. By the way, okay, let's take a look at the stability of these two systems. One of them is an accumulator, the other one is a differentiator. What is the absolute summation of this thing? It's absolute summation is summation of all ones from 0 to infinity. What's the summation of ones from 0 to infinity? Infinity. So this thing is unstable. An accumulator is an unstable system. How about this one? What is the absolute summation of 1 and minus 1? By the way, if you draw it, it looks like this. So what is the summation? 1 plus, but the absolute sum is necessary here. Absolute value of 1 plus absolute value of minus 1. It is 2, which is still less than infinity anyway. So this thing is stable. In many cases, that's something that can be encountered. Inverse systems, if one of them is stable, then the inverse system is usually unstable. This stabilization will be, equalization or inverse systems will be more important when we see frequency contents like the Fourier transforms that we will start perhaps next week. Next week, Monday, we have a lecture, right? On Tuesday, it is it's a holiday, but Monday and Tuesday. Very well, then I will put a doodle again to compensate for 3 hours, because we need that. Yeah, we will doodle it. You will choose again. You will vote for the. Yeah. But anyway, if you miss it, then you will all miss it, and it will be gone. Okay. Otherwise, some of you guys will attend, at least, and there will not be an attendance quiz anyway. Again, because some of you guys will not be available, certainly. But we will have to continue. The last years, I was checking out the complaints from the students on the internet, this APHIS system, if you know it already. On the APHIS system, one complaint from this course was the teacher is too much struggling to finish up all the content. And I do nothing but agree. I agree. Yeah, I'm struggling to finish the content, that's true. But that's necessary, because if you miss some of the contents, then it will be gone forever. So we'll try to finish. That's a pity, and I'm sorry about that. So I know, okay? But we have to finish. At least I'm trying to be accessible through the videos that has been recorded, so you can at least watch, I hope, okay? All right, stability is here. And the last property, yeah, let's not start with this property. It's the unit step response. Let's give a break of 10 minutes first, and then after the break we'll continue.